The idea of a sequence is just a list of real numbers. And we like to talk about these very abstractly, but we'll be seeing some very explicit formulas in a couple slides from here. The idea is that there's going to be some, there's going to be some first number followed by some second number, some third number, some fourth number, and so on. And as long as I don't know exactly what those numbers are, I'll just give each of them a name. And here I'm just using an A with a subscript indicating what order that number comes in the sequence. Now, if you like, since every positive integer will have, like a first entry, a second entry, and so on, every n will have an nth entry in this sequence. You can also think of a sequence as a function where your input is the integer n, and the output is the nth number in the sequence, the nth number in this list. All right, so that's very abstract. In order to get a bit more concrete, we need to at least agree on a notation for working with these things. And there's sort of three different flavors of this, all of them using these curly braces that come from set notation. So your choices are, you can talk about the first handful of items in the sequence and then trail off with some ellipsis there. Or inside the brackets, you can give a formula for the nth term of the sequence. And in certain cases, it's also useful to explain where the counting for the sequence starts and then show that this sequence is actually infinite. So in some of these things, we'll be able to actually come up with a formula and then work with the formula instead of having to juggle all of that information at the same time. So here is a sequence, and I've got three different ways of thinking about it. I can tell you that the formula for the nth term in the sequence is going to be n divided by n plus 1. So every number in this sequence is a rational number. And the first entry is going to be 1/2, 1 divided by 2. The second entry is going to be 2/3. And I know that if I want the number on this list at position n, whatever integer n is, that fraction will be n divided by n plus 1. Now, I can also write that in this middle form, where my a sub n is equal to n divided by n plus 1, and this formula governs every single entry in the sequence. And if you want to use the method of write out the first couple terms and then trail off with ellipses, it might look something like this, where we start 1/2, 2/3, 3/4, and then for convenience, we've also put the formula in here. So for some generic index n, again, the formula is n over n plus 1. Here's another example of a sequence. We have a different formula this time, so this defines a different sequence. Again, each entry in the sequence is going to be a rational number, but this time the formula is that the first term in the sequence is -1 to the power 1 times 2 divided by 3. The second term in the sequence is -1 to the power 2 times 2 plus 1 divided by 3 squared, and so on. You can check that the first couple terms of this sequence are going to be -2/3, +3/9, -4/27, and so on. And if I want to manipulate this sequence at all, it's much more convenient to look at the formula instead. Here's an example of a sequence where we cannot start at n equals 1 because the square root of 1 minus 3 is, well, the square root of negative 2. That is not a real number. But besides having to start somewhere else, I still have, this infinite list of numbers. This time it starts out at 0 and then 1, and from there on out, the rest of these entries in the sequence are these square roots. So sometimes these will be an integer and sometimes they will be irrational numbers. Now, where we're going with all this, I'm just talking about the notation right now. Where we're going with all this is that we'd like to manipulate sequences. We'd like to think about what happens as we progress further down this list. Is there anything intelligent we can say about sort of the limiting behavior of the sequence? And here's another example using the cosine function. So one of the ways we could visualize this information is by plotting out all of the different numbers in the sequence. We could either plot them out on the real number line. So maybe A1 equals a half, A2 equals 2/3, and so on. And just from this picture alone, it looks like the entries of that sequence are all congregating around the coordinate x equals 1. So this would be one way to visualize it just on the x-axis alone. The other thing you could do is this sort of graphing idea. I know the first element of the sequence is a half. The second element is 2/3. The third is 3/4, and so on. So here I'm really thinking of it as a function where for every integer input, I just graph the output as the associated y value. And again, this starts to look like, say, a function with an asymptote, just with the caveat that I'm only looking at these discrete dots rather than a continuous curve. Let's see now. So most of the homework today is concerned about limits of these sequences. So this is very much related to the kinds of limits that we work on in Calculus 1, the kinds of limits that we were using when we talked about improper integrals. Only here, my variable n only takes on integer values. So my n will only be, 1, 2, 3, 4, 5. It will never be a proper fraction. It will never be an irrational number. But the same idea as, as we go out further in the sequence, the numbers in that list start to congregate around the limiting value. So for this sequence right here, it's going to be 1. And if you look at this, if this was x goes to infinity, x divided by x plus 1, then that is something that we could have done in Calc 1 again. It's just, x over x plus 1 has a horizontal asymptote at y equals 1, and we are just calculating that out. So the technical definition of this limit looks very much like the definition for limit of a function. This is again thinking of the sequence as a function whose domain is, the set of positive numbers, positive integers. But the visualization shows us that, maybe we should be thinking about this formula for the sequence, well, for integers n, we do get some element of that sequence, some number on the list, but there's the epsilon definition for limits. The thing that I'm getting at here is that for calculation of limits of sequences, you really can just treat that formula as being a formula with the variable x, where x can be any real number as long as that formula is still defined. So the idea being that these points all lie on some curve governed by whatever formula the sequence has. The sequence only allows us to put in integers to that formula, but there's nothing actually stopping us from trying other values for the input. And then we're back to doing limits from Calc 1. So I want